All right, get ready, because today we're going deep on a question that's so simple, but also like mind-blowingly huge. Why does the universe look the way it does? And lucky for us, we've got this awesome YouTube video from History of the Universe to help us break it all down. It's going to take us from like our own planet to the edge of what we even understand about cosmology. So, yeah.
It really makes you think when you look at the universe on such a massive scale. It's not just stars and planets scattered randomly. There's this structure to it, this crazy web made up of galaxies and clusters and filaments.
So to get from like a random jumbled mess to this intricate web, we need to start with scale. Like, what's our cosmic address and what's it like to zoom out from Earth to the very edge of, well, what we can see?
Okay, so picture this. You start on Earth orbiting the sun, right? Then we zoom past the other planets through the Oort cloud, and we're not stopping there. We're going beyond our solar system into the local interstellar cloud. It's this region of gas and dust that's part of the Orion arm of the Milky Way galaxy.
Wow, we're already millions of light years away from home, and we haven't even left our own galactic neighborhood. So where do we go from there?
Next up, the local group. It's a bunch of about 50 galaxies, including our own Milky Way and that massive Andromeda galaxy. Fun fact, those two are actually on a collision course billions of years from now.
A galactic merger. Okay, that's something I wouldn't want to miss, but let's keep zooming out for now. What's bigger than a group of galaxies?
We hit the Virgo supercluster next, which has thousands of galaxies. And we're talking hundreds of millions of light years across. And even that is just one small part of Laniakea, which is this truly massive supercluster, almost 1 billion light years across. And it's here that you really start to see that cosmic web in all its glory. Superclusters all linked together by these filaments and separated by giant voids.
That is seriously mind-boggling. So if we're seeing this kind of structure from our tiny corner of the universe, does that mean it looks the same everywhere?
That's where the Copernican principle comes in. It basically says that Earth isn't in some special or privileged location. What we see should be pretty much representative of the universe as a whole.
So no matter where you are, you'd see a similar cosmic web.
Exactly. And we have evidence to back that up. Look at the cosmic microwave background, the CMB. It's like the faint afterglow of the Big Bang, coming from every direction. And it has this incredibly uniform temperature, around 2.7 degrees Kelvin.
So it's like a baby picture of the universe, all smooth and homogeneous, just 380,000 years after the Big Bang. But that creates a problem, doesn't it? How do we get from this smooth baby picture to the clumpy, structured universe we see today?
That's the big question. If the early universe was so homogeneous, why do we see galaxies and superclusters popping up later on? To figure that out, we've got to look at the forces at play, specifically this constant battle between expansion and gravity.
A cosmic tug of war, right? We've got the universe expanding, driven by forces we don't even fully get, like inflation in the early. And then there's dark energy, this mysterious force we observe today. And on the other side, we've got gravity, working tirelessly to pull it all back together.
Exactly. It's this push and pull that shapes everything, how the universe evolves, like this cosmic dance, expansion trying to spread things apart and gravity pulling them closer.
So how do we go from that smooth early universe, stretched out by inflation, to the galaxies and superclusters we see today? Did those structures somehow clump together even though everything was expanding?
It's actually even weirder than that. To understand how these structures formed, we need to get into, the mind-bending world of quantum mechanics.
Quantum mechanics. Okay, I'm always up for a little mind-bending, but, keep it grounded for those of us who aren't theoretical physicists.
I hear you. So picture the early universe, incredibly hot, incredibly dense, just packed with energy. And quantum mechanics tells us at this super tiny scale, things get fuzzy. There are these random fluctuations in energy field, like little ripples that pop up and disappear.
Okay, so tiny random ripples of energy in this hot, dense soup of the early universe. Where do we go from there?
Well, remember inflation, that period of super fast expansion. It didn't just stretch the universe, it stretched out these tiny quantum fluctuations too, like amplified them to astronomical scales.
Wait, are you saying those little ripples in the quantum foam got blown up to become the seeds of galaxies and clusters?
It sounds crazy, but that's the leading theory. Think of those ripples you see in a pond, right? A tiny pebble makes small ripples, but a giant rock makes massive waves. Inflation acted like that giant rock, taking those quantum fluctuations and turning them into density differences that gravity could work with.
That's incredible. It's like the universe used those tiny quantum hiccups to build itself from the bottom up. But how do scientists even picture the shape of this cosmic web, this giant sponge of galaxies and void? Didn't they used to think it was more like, meatballs or pancakes?
You're right. There was a huge debate about that, especially during the Cold. American and Soviet scientists had their own ideas. One side saw the universe as meatballs scattered in space, and the other saw it as pancakes of matter.
Meatballs and pancakes. That's a pretty delicious way to think about the universe. But what about the sponge model? Where did that come from?
Well, the meatball model, the one favored by American cosmologists like Jim Peebles, they imagined these clusters of galaxies just kind of clumped together like, well, meatballs in this like thin soup of empty space. It was bottom-up kind of approach. You start with small structures and they build up to the larger one.
Okay, I can kind of picture that. So what about the pancake model? Were the Soviets making cosmic crepes or something?
Not quite crepes, but yeah, they envision matter spread out in these flat, two-dimensional sheets or pancakes. And where these pancakes intersected, you'd get higher densities, and that would lead to galaxy formation. So it was more of a top-down approach, large-scale structures forming first, and galaxies kind of arising within them.
So it's like a cosmic pancake stack versus a cosmic meatball soup. I gotta say, the imagery is pretty great. But you mentioned a third contender, the sponge model. Who came up with that one?
That was Richard Gott, an American cosmologist who was actually inspired by the Soviet scientist Yakov Zeldovich. He pictured the universe as this complex, interconnected network, kind of like a sponge, with dense regions and voids all intertwined.
So not meatballs or our pancakes, but a cosmic sponge. It definitely seems like a more, I don't know, intricate and spongy way to picture the universe's structure. But how did scientists figure out which model was the most accurate? I mean, were they just looking up at the sky and saying, it's more like a sponge to me?
If only it were that simple. As our telescopes and sky surveys got better, we started getting a much clearer picture of how matter is actually distributed in the universe. And the data from these surveys, like the Sloan Digital Sky Survey, well, it didn't really support those early meatball and pancake models. What we were seeing was way more consistent with Gott's sponge model.
So science marches on, competing theories, new data, and then boom, a refined understanding of the universe. It's pretty cool. But we were talking about the Copernican principle earlier, the idea that the universe should look pretty much the same from any point. Does this sponge model hold up on those really vast scales?
That's where things get a little tricky. You see, there's this phenomenon called the end of greatness that kind of challenges our assumptions a bit.
The end of greatness sounds kind of dramatic. What's that all about?
Well, basically at a certain scale, around 1 billion light years, the universe starts to look homogeneous. All those distinct structures, the filaments, the voids, they kind of smooth out.
So it's like we hit a cosmic wall and everything just blends together. That's fascinating, but also a bit unsettling. Does this end of greatness mean the Copernican principle is wrong?
Not necessarily, but it does bring up some interesting questions. And it's connected to another mystery, the horizon problem. Remember the CMB and its super uniform temperature?
Yeah, it's like the universe was born with a perfectly even temperature, which is kind of weird when you consider how vast it is.
Exactly. The problem is there are parts of the CMB that should be way too far apart to have ever interacted, but they still have the same temperature. It's as if these distant regions somehow knew to be in thermal equilibrium, even though they were never in contact.
Okay, so how's that possible? Did they have some kind of cosmic phone call to coordinate their temperatures or what?
That's where inflation swoops in to save the day, or at least try to. The idea is that in the first fraction of a second after the Big Bang, the universe went through this crazy period of rapid expansion, like much faster than the speed of light.
Wait, faster than the speed of light? But isn't that like the ultimate cosmic speed limit?
It is, for anything traveling within the universe like matter and energy. But space itself, well, it doesn't play by those same rules. And this superluminal expansion during inflation could explain how regions that are now incredibly far apart were once close enough to interact and reach that same temperature.
So inflation stretched out the universe so fast that these distant regions, which were once all cozy and connected, got flung apart, but they still kept that initial temperature.
Okay, I think I get it, but it's still pretty wild to wrap my head around.
It is. But it's important to remember that inflation is still a theory. It solves the horizon problem pretty neatly, but we're still looking for that definitive proof. It's like having a suspect in a cosmic mystery novel, but we need more evidence to really crack the case.
Okay, I'm following the plot so far. We've got inflation stretching everything out and smoothing things over. But then how do we get from that smooth state to the clumpy structured universe we see today? Do those tiny quantum fluctuations we talked about earlier play a role? They're the stars of the show. Inflation stretched out those tiny quantum fluctuations, those random variations in energy fields, and blew them up to cosmic scale. They became the seeds of density differences, the blueprints that gravity could then use to build galaxies, clusters, and filaments.
So gravity took those amplified quantum ripples and was like, all right, let's make a universe.
It's amazing how something so small can lead to something so immense.
It really is. And there's another cool thing that gives us even more evidence for all of this. Baryon acoustic oscillation, or BAOs.
BAOs, that sounds a little intimidating. What are those?
Think of them as like giant sound waves, but instead of traveling through air, they traveled through this hot, dense plasma that filled the early universe.
So the early universe was like a cosmic pressure cooker with all these sound waves bouncing around.
Exactly. In that hot plasma, light couldn't travel freely. It was constantly scattering off these charged particles. But these density fluctuations created pressure waves, kind of like sound waves, that propagated through this plasma. Okay, so we've got these cosmic sound waves, these BAOs. What happened to them as the universe kept expanding and cooling down?
Well, as the universe cooled, it eventually reached a point where it became transparent. Protons and electrons combined to form neutral hydrogen atoms, and suddenly, light could travel freely. That's when the CMB was released.
So the universe went from opaque to transparent, like a fog lifting. And what about those pressure waves, the BAOs? Did they just fade away?
They got frozen in place. The photons carrying those pressure waves weren't coupled to matter anymore, so the waves stopped moving. But they left this distinct imprint on how matter was distributed in the universe.
So we can't see these ancient sound waves directly, but we can see their effects in how galaxies are clustered today. It's like finding fossils of those early cosmic sounds.
Precisely. The BAOs act as a standard ruler that cosmologists can use to measure the expansion history of the universe and double-check our models of how structures formed.
It's amazing how scientists can piece together the history of the universe from these subtle clues, like cosmic sound waves frozen in time. But we've been talking about gravity's role in all of this, and it makes me think about dark matter, something else we hear a lot about in cosmology.
Ah, yes, dark matter. The invisible scaffolding of the universe. This mysterious stuff that we can't see directly, but we know it's there because of how it affects visible matter.
It's always seemed kind of paradoxical. We can't see it, but we know it exists because of how it influences things we can see. It's like a cosmic ghost or something. Tell me more about how we even figured out that dark matter exists.
Well, the story of dark matter starts way back in the 1930s with this astronomer named Fritz Zwicky. He was looking at a cluster of galaxies and noticed something really weird. The galaxies were moving way faster than they should be, based on the amount of visible matter.
So it was like they were being influenced by some unseen force, some extra gravity that we couldn't explain.
Exactly.
Yeah.
Zwicky called this mysterious stuff dunkle materie, which means dark matter. His ideas were pretty out there at the time. But then, decades later, another astronomer, Vera Rubin, made even more compelling observations. She was studying how spiral galaxies rotate, and she found that the stars in the outer regions were moving way too fast, as if there was this invisible halo of matter surrounding each galaxy, providing that extra gravity to keep those stars from just flying off into space.
So it's like dark matter is the glue that holds galaxies together. And if it's playing a role in galaxies, does it also influence the structure of the universe on a larger scale?
Absolutely. Dark matter's gravity is crucial for how those initial density fluctuations we talked about grew into this vast cosmic web we see today. It's like a scaffolding, helping to pull matter together and shape those clusters and filaments and voids.
So dark matter is everywhere, even though we can't see it. It's like the invisible architect of the universe. But what is it? Really? Do scientists have any idea what this stuff is actually made of?
That's the billion-dollar question. We know it exists because of its gravity, but we still don't know what kind of particle or particles make up dark matter. It's one of the biggest mysteries in physics. There are a lot of theories out there, but one of the leading ones is this idea of weakly interacting massive particles, or WIMPs.
WIMPs, huh? So these, hypothetical particles, they'd have a lot of mass, which means they exert a lot of gravity, but they'd rarely interact with normal matter. I guess that explains why they've been so hard to detect.
Exactly. There were experiments happening all over the world, underground labs, particle colliders. Everyone's looking for any sign of WIMPs or other dark matter candidates. It's like a real detective story, and the clues are super subtle.
It's wild to think about this invisible stuff shaping the universe all around us. Makes you wonder what else we might be missing, what other mysteries are out there covered.
That's what's so cool about cosmology. There's always something new to find. Speaking of discoveries, did you know that everything in our local supercluster, including the Milky Way, is moving in the same direction?
Whoa, seriously, we're not just floating around randomly. Where are we all headed?
Towards this mysterious region of space called the Great Attractor.
The Great Attractor. That sounds kind of ominous. Is it like a cosmic vacuum cleaner sucking up everything in its path?
Not exactly, but it is a region with a lot of gravitational pull. Scientists first discovered this large-scale movement when they were studying the CMB. They realized that our local group of galaxies is moving at about 600 kilometers per second relative to the CMB.
So we're definitely not standing still. It's like we're caught in some cosmic current. But what is the Great Attractor itself? Is it some giant black hole or a massive cluster of galaxies?
It's actually a really dense region of space with a ton of galaxy clusters, including the Norma cluster, which is supermassive. But here's where it gets even more interesting. Even the Great Attractor is being pulled towards something even bigger.
Wait, there's something bigger than the Great Attractor. What is this, like a cosmic hierarchy?
You could say that. It's called the Shapley Supercluster, and it's about 650 million light years away from us. It's got thousands of galaxies, and the estimated mass is equivalent to like 10,000 Milky Ways.
Wow. That is a lot of galaxies and a lot of gravity. So the Great Attractor is just a pit stop on our way to this even grander destination. Huh.
Exactly. But there's another thing going on here, too, the dipole repeller.
The dipole repeller. Okay, that sounds like something straight out of science fiction. What is that? Some kind of anti-gravity force that's pushing us away from certain regions?
Not quite anti-gravity, but it's close. It's this huge region of space that's basically empty, a cosmic void. And because it has less mass than the areas around it, its gravitational pull is weaker.
So it's not actively pushing us away, it's just not pulling as hard as other regions.
Right. And this difference in gravitational influence, well, it affects how galaxies move overall. We're being pulled toward Shapley, but we're also being subtly influenced by this weaker pull from the dipole repeller.
It's incredible how these giant structures, hundreds of millions of light years across, are all connected and influencing each other's movement. It really makes our little corner of the universe feel pretty insignificant.
It definitely puts things in perspective. But even with all we've learned about the universe, there are still so many puzzles to solve. For example, have you heard of the axis of evil?
The axis of evil. Okay, now that does sound a little creepy. What's so evil about it?
It's not actually evil, but it refers to this weird alignment between certain features in the CMB and, well, our solar system.
So there are patterns in the CMB, the afterglow of the Big Bang, that seem to line up with our solar system. That's pretty weird, isn't it?
It is, and it's something that could challenge the Copernican principle, the idea that we're not in some special place in the universe. If that's true, then why would there be this strange alignment?
Yeah, it does seem like a pretty big coincidence. So what do scientists think is causing this axis of evil?
Honestly, it's still a mystery. Some think it might just be a statistical fluke, pure chance. Others think there might be some deeper physics going on that we haven't figured out yet.
Another puzzle to add to the cosmic to-do list. It seems like the more we learn about the universe, the more questions we uncover.
Exactly. And that leads us to one of the most mind-boggling concepts in cosmology, the multiverse.
The multiverse. Okay, now we're really getting into science fiction territory. Are we talking about parallel universes and alternate realities?
Well, it might sound like science fiction, but there are some theoretical frameworks like string theory and eternal inflation that suggest our universe might not be the only one out there. There could be a whole multiverse with tons of other universes, each with its own set of physical laws and maybe even its own forms of life.
So there could be an infinite number of universes bubbling out there, and we're just one tiny bubble in this cosmic foam. That's a pretty wild thought.
It is. And some scientists believe that by studying the CMB, we might even find clues about the existence of other universes. Imagine finding evidence of a collision between our universe and another one.
Whoa, that would completely change how we see reality. So we've gone from exploring our cosmic address to pondering the possibility of a multiverse. It's been quite a journey. What was the most interesting part for you?
For me, it's just the incredible interconnectedness of everything. From those tiny quantum fluctuations to the vast cosmic web and this mysterious dance of dark matter. It really shows us how much we still don't know, but also how much we've been able to figure out. It's pretty awe-inspiring.
Totally agree. And it makes you wonder what other amazing discoveries are still out there just waiting to be made. What do you think the future holds for cosmology?
Who knows what breakthroughs are coming next, but one thing's for sure, that quest to understand the universe and our place in it, it's going to keep inspiring scientists for a long time.
Well said. And on that note, we've reached the end of our deep dive structure of the universe. We covered a lot of ground, explored some huge mysteries, fully got you about. Thanks for joining us on this cosmic adventure.